Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifpat.me. You can click the appropriate link under the this lecture resource column over here to view the notebook in NB Viewer and run it online in Binder. The other way is to download the notebook from the course GitHub account RFUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888, and here is the notebook for lecture number 4.2 of the fourth module, Mathematics and Statistics, for the course titled Tools and Techniques for Data Science. Well, my dear students, in the last session we have covered in detail the descriptive statistics part, and today we are going to see the details of inferential statistics. So before proceeding, let me give a quick comparison. Well, in the previous session, we have seen that descriptive statistics is used to describe, summarize, and present different data sets through numerical calculations, tables, and graphs. We have practically seen as how we can calculate the three measures of center, mean, median, and mode, the four measures of spread, range, IQR, variance, and standard deviation, and the two measures of asymmetry, skewness, and kurtosis. And today we will try to understand inferential statistics, that is used to make inferences and predictions for an entire population based on sample data from that population. My dear students, let me also differentiate between the two terms that I have used, prediction and inference. Suppose I saw a boy wearing untied shoes, and I predicted that the boy will fall. Later, when I saw that boy crying, I inferred that the boy has fallen down. So this is the difference between prediction and inference, with a real life example. Okay, let's move ahead. Please do install SciPy, Stats Model, and Statistics libraries for this notebook. Other than NumPy, Pandas, Matplotlib, and Seaborn, which I think you all have already installed on your systems. Let me import these modules. And here is the agenda for today's notebook. My dear students, it is a long agenda, and I have divided it into three sections. The first section deals with the important basic probability concepts required for machine learning. The second section deals with hypothesis testing and different types of tests, parametric as well as non-parametric. This third section is actually a journey from variance to covariance to correlation and finally to regression. My dear students, if you want to learn a specific topic, you can always click the topic from the table of contents in the description box below. Okay, so let's start with the overview of the probability concepts that one must know before starting the journey in the domain of machine learning. Let me start by revising some of the very basic probability concepts. Well, my dear friends, we all know that probability defines the likelihood of occurrence of an event. It is the ratio between the favorable outcomes and the total number of outcomes, whose value can lie between 0 and 1. To understand the probability, we normally start with predicting the outcomes of at times tossing a coin, maybe rolling a dice or maybe drawing a card from a pack of playing cards. And later we apply the same concepts in the domain of artificial intelligence and machine learning. Before showing you some examples, remember there are two types of events. Uh, Independent events like rolling a dice twice, an event that does not impact the other. Dependent events, an event that impact the other. For example, drawing two cards from a pack of playing cards without replacement. And here are some very basic examples for your review. Note the probability of drawing a card of ace is 4 over 52, because the total cards are 52 and the ace cards are 4. Similarly, the probability of drawing a card being ace or spade is 16 over 52, because in this example the favorable outcomes are 13 cards of spade plus 3 additional aces of clubs, diamonds and hearts. So it makes up 16 over 52. Please go through with these examples before moving ahead. Well, my dear students, joint probability means the probability of two events happening together. Let's talk about the joint probability of independent events first. Well, if two events A and B are independent, we can use the probability rule of product to find out the probability of intersection of these events, or the probability of these events happening together. My dear students, there are some of the examples over here in which I have calculated the probability of getting two consecutive heads from two tosses, three consecutive heads from three tosses, exactly two heads from three tosses, and at least two heads from three tosses. Please go through with these examples. I have prepared the total sample space for each event as well. I think you will be able to understand this. Okay, in this first example, I have calculated the probability of getting three consecutive heads from three tosses, but this time I have not created the sample space for the three tosses. Rather, I have used the probability product rule. So I have multiplied the probability of getting a single head and two heads, and I have got the result. This will make more sense in this third example, this one, where I have calculated the probability of 10 consecutive heads from 10 tosses without creating the sample space of 1024 possible events. Instead, we take the product of probabilities that we have already calculated, and we got the result. That's great. Now a $100 question is, what is the probability of getting 5 consecutive heads from 100 tosses? Well, the total sample space will be 2 raised to the power 100, but how to calculate the count of favorable outcomes, and that too without creating the entire sample space? Of course, it is difficult to create that much big sample space. Well, combinatorics come for our rescue in this scenario. My dear students, we can compute the number of outcomes of an event using the number of combinations equation. And this number of outcomes or number of combinations equation can be read as n choose k, which equals to n factorial divided by k factorial and n minus k factorial. Let's see this example. Okay, we want to calculate the probability of two heads in 3 coin flips. So the favorable outcomes can be calculated as 3 choose 2, which comes out to be finally 3. and the total sample space is naturally 2 raised to the power 3. So the probability of this event is 3 over 8, that is 0.375. My dear students, this is an other example. Please work this out before moving ahead, since you all have done this in the undergrad course, so I'm not going into the much details. I hope these examples will make your concepts clear about the combinatorics. Let me practice this with Python code as well. So let us suppose that I want to calculate the probability of getting exactly 2 heads in a 10 coin toss experiment. Or maybe the probability of getting exactly 5 heads in 10 coin toss experiments. Well, my dear students, over here I have written a function for this that receives two arguments, n and k, where n is the total number of experiments and k is the number of heads or tails. Note that to calculate the numerator, we can use the factorial function of math module and do it the long way, or simply use the COMB combination function of the math module to calculate the combinations. The denominator should be the total number of outcomes, which in this case of a coin toss experiment will be 2 raised to the power n, as shown over here. Finally, this function divides the numerator with the denominator and return the probability. I hope this function is clear. Let me first execute this cell and then execute the code of this cell. So great. So this is the probability of getting 2 heads, and this is the probability of getting 5 heads. Let me put this 5 over here. Yes, great. Okay, so before I proceed, let me use this function in a loop or in a list comprehension to calculate 11 different probabilities of getting 0, 1, 2, 3 and so on to 10 heads in a 10 coin toss experiment. So over here, if you can see that I have used this loop from 0 to 10 times, and I have called this probability calculator function. So let me check out. And the same can be implemented using the list comprehension. If you are comfortable with this, this is the Pythonic style. Well, my dear friends, you can note that the probability of getting 0 and 10 heads is minimum, and it is same, while the probability of getting 5 head in a 10 coin toss experiment is maximum, and that is this one, 0.24609. My dear students, with this background, we are ready to take on another important probability concept, and that is law of large number. Great. My dear students, we all know that when we flip a coin, the probability of getting heads is 50%. This is called theoretical probability. Let us suppose you do an experiment and flip a coin 4 times. As per the theoretical probability, you should get 2 heads and 2 tails. However, this happens very seldom that your experiment outcome exactly match the theoretical outcome. Let us check this out using this binomial method of random module of NumPy library. Well, this method binomial is passed two values, n, which is the number of experiments you want to perform, and P, which is the probability of success. This method draws samples from a parameterized binomial distribution. Let us run the code of this cell, and let me run it again and again and again and again. You see, there are different values, and let me make it more clear by increasing the number of experiments from 4 to let's suppose 10,000, and let me execute the code of this cell now again and again. Have you noticed anything? Well, this is what the law of large number is. That is, the more experiments we run, like in this example 10,000, the closer we get to the theoretical or expected probability, that is 50%. You see, 10,000 experiments and almost around 5,000 times we are getting the heads. Let me run this. Over here we are running it 4 times and the outputs are 2, 3, 3, 3, 1. So it is not very close to the theoretical probability or the concepts which we have discussed. Okay. For more clear understanding, let me show you another example. Okay, this one. I have created a NumPy array of around 11 numbers. Note the first 4 numbers are 1, 2, 3, 4 small numbers, and the last 4 numbers are quite large, 2 raised to power 15, 2 raised to power 16 and so on. These are the number of experiments that I want to perform. So I am passing this array to the binomial method. So this binomial method will run the experiment for 1 time, then 2 time, then 3 time, 4 time, 5 time and so on, and will return the count of the number of heads in this variable heads count. So this variable will finally have these probably 11 outcomes of these 11 experiments, and then I have divided it with the number of experiments, the head count, to find the proportion or probability of head, and here is the output. Fine. Now my dear students, you can note that the probability when we run this experiment large number of times is quite close to the theoretical probability, 0.5, 0.5, 0.4 and 0.4. But when we run this experiment less number of times, the probability is not very much close to 50%. Over here it is 0, over here it is 1, and then over here it is 0.8, then 0.3, and then 0.2 and so on. So I have tried my best to make you understand the law of large number. I hope with these examples you will never forget the law of large number. Now let me move ahead. Okay, so fine. Let's now discuss and understand bias theorem, one of the most important topics in the domain of machine learning and natural language processing. Instead of straight away jumping onto the topic of Bayes' theorem, let me quickly brush up your concepts of marginal, joint, and conditional probabilities. I think we have already discussed the marginal and this joint probability, so let me talk about the conditional probability. Well, conditional probability is the probability of an event A given that event B has already happened. Its formula is shown over here, which equals the probability of intersection of the two events divided by the probability of B. And if the two events are independent, probability of A intersection B can be written as product of probability of A multiplied by probability of B. Let's see this example. Suppose the probability of a student getting an A grade in exams is 0.15. My dear students, if I ask you that a student has studied for 5 hours daily in the entire semester, what will be his or her probability of getting an A grade? Naturally, you will say that the probability will increase in that case. Similarly, if I ask you that a student has studied for just, let's suppose, 5 hours before the exam only and never in the entire duration of the semester, what will be his or her probability of getting an A grade? And naturally, you will say that the probability this time will be far less than 0.15. Okay, my dear friends, do go through with these examples for a crystal clear understanding of conditional probability. And let me move ahead to the Bayes theorem. Well, Bayes theorem by Thomas Bayes is a way of calculating conditional probability without the joint probability. And to calculate the probability of an event A, given that event B has already occurred, we use this conditional probability formula. So probability of A given B equals probability of A intersection B divided by probability of B. And similarly, it can be written vice versa as well. That is, probability of B given A equals probability of B intersection A divided by probability of A. And probability of B intersection A naturally can be written as probability of A intersection B. So these are the two equations. We can rewrite these two equations as like this, equation 3 and equation 4. And if we equate equation 3 and equation 4, which are both equal to A intersection B, we can rewrite them like this over here. And finally, if we divide both sides of this equation where my mouse is hovering by a probability of B, we get this shape. Probability of A given B equals probability of B given A multiplied by probability of A divided by probability of B, provided that probability of B is not equal to 0. And this is the Bayes theorem. My dear students, in this equation, this probability of A given B on the left hand side is known as the posterior probability. This probability of B given A is the likelihood. This probability of A is the prior probability. And in the denominator, this probability of B is also known as normalization constant. Okay, so with this formula of Bayes theorem in mind, let's move on to the example. Okay, so the example is, what is the probability that that a card drawn from a deck of playing cards is a queen, given that it is a card of spades. So let me write it as, let's suppose that Q is the event, the card is queen, and S is the event, that card is spade. So the probability of getting a queen, given that the card is a spade, will be equal to something like this, which is the Bayes theorem. So probability of Q given S is equal to probability of S given Q multiplied by probability of Q divided by probability of S. Now this probability of S given Q is 1 over 4. How? My dear students, we already know that the card is a queen and there are 4 queens in a deck of 52 cards. So the total sample space is reduced to 4. So that is why we have a denominator 4. And now since we know that the card is a queen, so the number of favorable outcomes is 1. So the probability is 1 over 4. And the probability of getting a queen is simple, since there are 4 queens in a deck of 52 cards, so 4 over 52. And similarly, the probability of getting a card of spades is also simple, since we have 13 cards of spade in a deck of 52, so we have 13 over 52. So the overall probability of getting a queen, given that it is a spade, is 1 over 13. Well, my dear students, do go through with this example as well. to have a clear understanding? Well, there are a lot of applications of naive Bayes theorem. My dear students, naive Bayes algorithm is extensively used in machine learning and natural language processing. In the problem solutions of spam email classification, sentiment analysis, recommendation systems, article categorization, search engines, and detection of inappropriate comments as well. Okay, so let us do an example and use a naive Bayes algorithm to classify spam emails. Our target is to design an algorithm which, when provided with a text message, should be able to classify it as either ham or spam. And where ham is normal message while spam is a non-desirable message, aiming to distract the user attention. Other than accuracy, our algorithm need to be fast so that it can filter out the ham and spam messages in real time. Okay, so the baseline of this algorithm is that there are certain words that mostly come in the spam emails, like the word win, money, free, and so on. And at the same time, in our regular emails or ham emails, uh, you will mostly find words related to your work and interest. And if you are a student, there would be words like lecture, notes, assignments, and so on in your emails. Okay, let's suppose that we have 40 emails, and we know that 20 of them are spam and 20 of them are ham. We have gone through the spam emails and have find out the count of some important words appearing in them as shown over here. Uh, the word dear appeared 3 times, this win appeared 9 times, money appeared 8 times, and so on. And there are a total of 30 words that I have selected. And similarly, we have repeated the same process for the ham emails as well. So in these 20 ham emails, the word dear appeared 5 times, lecture 7 times, notes 9 times, assignment 6 times, and so on. And now let's suppose after segregating these 40 emails into 20 spam and 20 ham, and these word counts with us, we want to classify an email having this message. Dear students, I am writing to inform you about tomorrow's free workshop. So this is an email message, and we want to classify it whether this is a ham email or spam email based on this data. If we classify it ourselves, we will naturally see that this is a ham message. Let us now see how our algorithm will classify this using the naive Bayes classifier. Okay, in this message, our algorithm will naturally pick the two words dear and free, which are underlined over here. And let's suppose that H stands for ham, S for spam, D for dear, and F for free. So we need to compute these two probabilities. Probability of ham given that the message contains the words dear and free. The probability of spam given that the message contains the word dear and free. And as per the Bayes theorem, these can be written like this. Great. My dear students, since the denominator of these two are same, that is probability of D comma F, or you can say that probability of D intersection probability of F, so we can ignore this. Let me move down. Okay, fine. So if we ignore the denominator, we are left with the numerator only, and we can simplify this numerator like over here, this probability of getting the word dear and free, given that it is a ham, can be written as probability of getting the word dear, given that it is a ham, probability of getting the word free, given that it is a ham, multiplied by probability of ham. So we can rewrite it like this. My dear friends, the naiveness in our algorithm is the assumption that the order in which the words appear in this message are irrelevant. So the word dear is coming before the word free. This is irrelevant. Remember, this is what the naiveness is in this algorithm. This is the naive part of bias theorem, which makes our calculation easy, thus making it efficient. Okay, so let me talk about this. Probability of the word deer, given that it is a ham, so come up over here. So the probability of word deer in this is 5 over 30, which is written over here. Probability of getting the word free, given that it is a ham, come up over here. We have the count of free is 3 divided by 30, so this is what the probability is. And the probability of a message being ham is, of course, 20 divided by 40, which is over here. Similarly, the probability of the word dear, given that it is a spam, is dear 3 over 30. And probability of getting the word free, if this is a spam, this is 1 over 30. And naturally, the probability of spam is 20 divided by 40, which is shown over here. So the conditional probability of a message being a ham is 0.0083, while the probability of this message being spam is 0.0017. And therefore, our classification algorithm that uses the naive Bayes theorem will classify the given message as ham message, as its probability is higher. My dear friends, with this background of Bayes theorem and its application of uh, ham and spam classifier, I think you will be able to apply it in different problem scenarios of machine learning and natural language processing that you will come across in the future courses that you will study in this degree program. Okay, so far so good. Let's move ahead. Okay, how probability relates with statistics. Probability and statistics. Well, this is a course that is being taught in almost all undergrad programs of computing like CS, SE, IT, and data science as well. However, whenever I asked any of my students to differentiate between the two, he is a bit confused. My dear students, remember, probability deals with the prediction of future events, while statistics is used to analyze the frequency of past events. Moreover, probability is the theoretical branch of mathematics, while statistics is the applied branch of mathematics. Let us understand this with an example. Let me use the binomial method of a random module of NumPy library. This time I have passed it 3 arguments. The n, this is the number of coins that I want to flip at a time, which is 5. P is the probability of getting head, which is 0.5. And size is the number of times I want to repeat this experiment. And let me execute the code of this cell. Well, it has returned me an array of 100 values, and each value represents the number of heads that turned up in each experiment. So we have very less number of zeros, 0 heads, and of course very few number of 5 heads. Okay, so let us calculate the frequency of getting a 0, 1, 2, 3, 4, and 5 heads. And for this we can use the unique method of NumPy by passing it the array head counts. And if we want to get the frequency of each of the unique values of head counts, we need to set this return underscore counts argument to true. Let me execute the code of this cell. So these are the unique values in this array 0, 1, 2, 3, 4, 5, and these are the counts. So this value of 2 shows that we have got 0 heads twice, and over here as well this value of 2 shows that we have got 5 heads twice, and this 38 over here shows that we have got 2 heads 38 times. I hope this output is making sense to you all. So with this background, let me tell you what do you mean by probability distribution. My dear students, a probability distribution is a statistical function that describes all the possible values, in this case 0, 1, 2, 3, 4, 5, and the probabilities or likelihoods that a random variable can take within this given range. So that means this is a probability distribution. Let us draw a probability distribution graph of this experiment by dividing this variable frequency containing these values with 100, which is the count of the experiments to get the probability. And let me use the bar chart and show you the graph. Well, great. Over here you have the head flips: 0 head, 1 head, 2 head, 3 head, 4 head, and 5 head. And over here we have, along the y-axis, we have the event of the probability, event probability. And naturally from here you can observe that the probability of getting 0 heads and 5 heads is quite less, around 0.02, and the probability of getting 2 heads is the maximum, that is 0.38. Okay, so now once again, the stage is set for you to understand another topic, and that is the probability distributions. And probability distributions can be of two main types depending on the type of variable we are dealing with, that is discrete or continuous. Let me first talk about probability distributions for discrete random variables. My dear students, discrete probability distributions are used to model probabilities of discrete random variables or variables that are counted and not measured. There are different types of discrete probability distributions like binomial, Bernoulli, multinomial, and Poisson, each having its own probability mass function called PMF. You can describe the discrete probability distribution by a graph as shown over here. And in this graph, the height of the bars represent the probability of that specific value. Okay, let me move on to probability distributions for continuous random variables. Excuse me. Well, continuous probability distributions are used to model the probabilities of continuous random variables or variables that are measured, not counted, like weight, height, distance, and so on. There are different types of continuous probability distributions like this normal distribution, exponential distribution, students t distribution, chi-square distribution, and so on. And of course, each of these have its own probability density function, PDF. You can describe the continuous probability distribution by a graph as shown over here, which shows the probability distribution for a continuous variable, in this example, the amount of tip. The amount of tip given by customers in the restaurant, which ranges from $0 to probably $10. My dear students, in discrete probability distribution, graphs, the probability of a specific event, for example, getting four heads, can be found by the height of this bar. So the height of this bar is this 0.15 or 17 or 18. On the contrary, in case of the continuous probability distributions, we compute the probability between a range of values, which is the area under that specific portion of the curve. And of course, the entire area of the curve above the x-axis equals to 1. This is one of the more important property of continuous probability distribution graphs. Okay, I think that's enough. Whenever you have time, please do explore different probability distributions. And today we will discuss one of the most commonly used distribution called the Gaussian or the normal distribution, also famously known as the bell curve. And this was proposed by Frederick Gauss. My dear students, this is the PDF or probability density function or formula of normal distribution that is defined by its mean and standard deviation. If you closely observe this graph over here of normal distribution, you can see it is a symmetrical graph with its center at the mean. And moreover, this 68% of the data exists within one standard deviation from the mean. 95% of the data exists within two standard deviation from the mean, and 99.7% of the data exists within three standard deviations from the mean. Great. Let me describe this with an example over here. Well, over here I have used the normal method of random module of NumPy library, and this call is going to generate 10,000 random values having a mean of 25 and a standard deviation of 3. Well, later I have used this disk plot method of Seaborn to draw the histogram of this dataset to visually see how this dataset is spread. I've used the AXV line to draw vertical lines at the mean and at the first, second, and third standard deviation. Let me run the code of this cell. Great. So you can see that we requested to get data having mean at 25 and standard deviation at 3, and this is what we have got. This yellow line is the line at which the mean resides. This purple line on both sides is showing the first standard deviation, green the second standard deviation, and this red is the third standard deviation. Okay, so remember in between these two lines, red lines, which shows the third standard deviation, 99.7% of the data resides, which is quite apparent from this graph as well. Let me move ahead. Okay, my dear students, another very closely related distribution to the normal distribution is the Z distribution, which is a normal distribution having a mean of 0 and standard deviation of 1, as shown in this graph over here. You can see the mean is 0 and the standard deviation is 1, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. Great. Okay, consider this normally distributed data set shown in this left table, and over here just consider this column, the body weight column, having these body weights with the mean of 73 and standard deviation of 10.16. This is a normally distributed data. Let's make it standard normal, let's make it standardized, or let's make it as per the Z distribution using this formula, Z is equal to x minus mu over sigma. So to convert this to a Z distribution, you simply subtract each value from the mean, that is 73. So you subtract 86 from 73 and get 13. You subtract 82 from 73 and get 9, and so on. and later you divide these values with the standard deviation, that is 10.16, to get this value. For example, we divide 13 by 10.16 and get 1.28. We divide 9 by 10.16 and get 0.89. So this is the standardized data. This column of body weight, or this column is now standard normal distribution or Z distribution, because it is having a mean of 0 and standard deviation of 1. Okay, so let me go through with a very quick example. Suppose there are 10,000 students in my data science class. First of all, I'm actually generating the random result of the students with the mean of 60 and standard deviation of 10 using the normal method. You see this. So this is the result of the students having a mean of 60 and the standard deviation of 10. Okay, let's suppose that a student has scored 85% marks and I want to calculate the Z-score. So let me do that. So this is the mean, and to calculate or to convert the 85 marks into a Z-score, I have used this formula, x minus mu over sigma. X minus mu over sigma. So this is the Z-score, and the Z-score is 2.5. So that means 2.5, 1 sigma, 2 sigma, 2.5, somewhere over here. Great. So let me calculate how many students are above this student using the np.where method. So it says that there are 59 students above him. And let me plot the graph for this. And this is the graph. Once again, I have used the displot method. Note this purple line over here. This is the place where the student with the 85% marks reside, and you can note that very less number of students are there, around 59, which are above him. The student has got 85% marks. Great. Let me repeat the same example with a little bit of different data this time. Over here, I'm assuming that the 10,000 students of data science now they have got better results. Like their mean is at 90 with a standard deviation of 2. So I've used the normal method again to generate the random results of those 10,000 students with a mean of 90 and standard deviation of 2. Let me run this. Great. And now once again the same student has got 85% marks, and now I want to know how many students are above these students. Once again I am converting the 85 marks to the corresponding Z-score, and this time you see the Z-score is minus 2.5. So if I come up once again over here, so that means this time the students reside somewhere over here, minus 2.5. Let's draw the specific graph for this, the way we have done before. So this is the graph. And this purple line this time shows that this student resides somewhere over here. So now he has gone quite much down. And once again, if I check out how many students are below him, the number of students below him are 66, I think. So 9934 students are above. So 66 students will be below him. My difference, you might have got a fair idea now that how the data is distributed and how the mean and standard deviation do impact the distribution of the data. Okay, before moving ahead, let me give you a comparison between the Z-score and its corresponding p-value, also called the probability value. First of all, this right graph over here shows the marks of 10,000 students, data science students. And you see this is a normal distribution, a bell curve, because it is having a mean of 60 and standard deviation of 10. This graph over here shows the corresponding Z distribution having a mean of 0 and standard deviation of 1. My dear students, In the above two examples, only 59 students attained z-score above plus 2.5, and only 66 students attained a z-score below minus 2.5. If you can recall, you see. We can convert this z-score, that is the plus 2.5 and minus 2.5, to a p-value using this formula. Or you can always use a calculator. Online calculators are available. You can visit this link, Statology. There are a lot of calculators which are available. Do check out these calculators. And right now I'm interested in a calculator that will convert my z-score to a p-value. Let me write down 2.5, let's suppose, and let me calculate. So the value is 0.0124. Let me check this out. So 0.0124, that is 0.0125 roughly, or 1.25%. Great. I hope this is making sense. More on this in the hypothesis testing part, inshallah. Okay, so next is the central limit theorem. My dear students, if you have a population with a mean mu and standard deviation sigma, and you take sufficiently large random samples from that population with replacement, then the distribution of the samples mean will be approximately normally distributed. This is what the central limit theorem says. So this is quite Greek to many of my students. So let me show you this with examples. So over here I'm using the normal method to generate a data set of 10,000 values which are normally distributed. X1 is the variable containing all these values. In the trial one, what I'm doing is I'm generating a random sample from this distribution above, X1 of size 10, and that too without replacement. Let me take that, you see. So I have taken 10 values from this, and of course these are not distributed normally. You can see this from the graph. Let me this time use a function. This function is passed the population distribution from which we want to draw the samples. N is the number of samples to be drawn, while this size is the size of each sample. What this function is going to do, this function is going to return a list of means of all the samples. I hope this code is making sense to you all. Let me run another trial or experiment now, and this time I am calling the displot method, and I'm calling this function with these values, and I'm passing the same distribution x1, that is this normal distribution. I'm passing this distribution to this function, and I am generating 10 random samples of size 10 each, and I'm plotting that. Once again, this is not normally distributed. Let me increase the size now. This time again, I am calling that function with the same distribution, that is x1. I need to draw samples from this, but this time I am drawing 100 samples of size 10 each. You see? And let me repeat this experiment for 1,000 times. Let me run it. So you see now this is normally distributed. So this is what the law says. And the law says, if you have a population with mean mu and standard deviation sigma, and you take sufficiently large random samples from this population with replacement, then the distribution of the sample means will be approximately normally distributed. So this was the population, normally distributed population. If I get a sample of, let's suppose, size 10, it is not normally distributed. And if I increase the sample size to, let's suppose, 1000 over here, it is normally distributed. The beauty of this will be apparent when you will see this example. This is not a normally distributed data. This is a skewed distribution, and I have kept all these values in a variable x2. Let me draw a sample of size 10 samples of size 10 from this distribution, take the mean of all those samples and populate it and draw it in a histogram fashion. And of course, this is not normally distributed. On the contrary, if I increase the number of samples to 10,000 of size 10, and you will see that this time it will be perfectly normally distributed. Let me repeat this for a multi-model distribution as well. Let's suppose this is a multi-model distribution, and let me generate 10 samples from this of size 10 each, compute their mean and draw the histogram. And of course, this is not normally distributed. And if I increase the number of samples to, let's suppose, 10,000 and draw it from that bimodal distribution, you see we have this normally distributed graph. This is what the central limit theorem is. I hope I have shown it practically by running different pieces of codes and the graphs. Now you should have a fair idea about central limit theorem. Okay, so I think, my dear students, we are now very well equipped to move on to the next section, and that is hypothesis testing. Well, a hypothesis is actually an idea that can be tested. For example, a biologist believes that a certain pesticide or fertilizer will cause the crops to grow more in 1 month than they normally do. Similarly, maybe a company believes that spending more money on digital advertising will lead to increased sales than the normal sales. So, hypothesis testing is the process of evaluating two mutually exclusive statements on population data using sample data. Let's suppose that one of my colleagues says that higher education is very expensive in Pakistan. This is an idea or statement that can't be tested. However, if we define expensive as any cost higher than, let's suppose, a million Pakistani rupees, then it immediately becomes a hypothesis that can be tested. Okay, so the next $100 question is how to do hypothesis testing so that we can either accept or reject the hypothesis. My dear students, I have divided the hypothesis testing in these 6 steps, although just 4 are shown in this image. First of all, we need to formulate the hypothesis, a null hypothesis, and of course, an alternative hypothesis. Next step is to collect or gather the data from the population using any of the techniques that we discussed in our previous session, like random sampling, systematic sampling, or stratified sampling. Next, we need to select the appropriate test to test the hypothesis. Then we execute the test, and based on the test result, we make a decision. And finally, we check for errors, if any. Let's now go through each of these steps one by one. Let us first understand the difference between the null hypothesis represented by this H0 and the alternative hypothesis represented by HA or H1. In hypothesis testing, if you want to reach to a conclusion, we have to make 2 statements in such a way that if one statement is true, the other will automatically be wrong. The concept of null hypothesis is similar to innocent until proven guilty. You can also think of null hypothesis as the status quo. The alternative hypothesis is also called the research hypothesis, which is the claim to be tested. A researcher actually proposes the alternative hypothesis and then tries to reject the null hypothesis. Let us understand this with examples. Suppose there is a teacher who believes that a certain teaching technique will affect the mean score of students in his subject of, let's suppose, data science. The teacher is not sure whether this technique will increase or decrease the mean score, which is, let's suppose, currently 65. So the null hypothesis or the status quo says that after applying the new teaching technique, the mean score stays the same, that is 65%. The alternative hypothesis, the research hypothesis says that the mean will change. It will either go up or down from this current mean. Well, to prove this research hypothesis, alternative hypothesis, the teacher applied the new teaching technique on his class. After the semester result, he applies an appropriate type of hypothesis test to see if he can reject the null hypothesis. And since this alternative hypothesis has a not equal to sign, so the test will be a two-tailed test or a non-directional test, because the teacher can test for effects in both the directions. This is what is shown over here in this graph, and more on this in a while. Let's move on to another example. Suppose a biologist believes that a certain fertilizer will cause the plants to grow more in 1 month than they normally do. And the current mean growth rate of plants per month is less than or equal to 5 centimeter. So the null hypothesis in this case, which is the status quo, says that the fertilizer will have no effect on the average growth of plants and will stay the same, that is less than or equal to 5 centimeter. The alternative hypothesis or the research hypothesis says that the fertilizer will improve the growth rate of plants. So you can see HA mu is greater than 5 centimeter. And to prove his research hypothesis, the biologist takes a few plants to his laboratory, apply the fertilizer on them, and after 1 month collects the data, and finally apply the appropriate test to see if he can reject the null hypothesis. Note, since the alternative hypothesis has a greater than sign, so the test will be one-tailed test or a directional test, or more precisely a right-tailed test because of this greater than sign. This is what is shown in this graph. And more on this in a while, and let me move on to a third example for better understanding. Let's suppose a doctor believes that a new drug will be able to reduce the blood pressure in his patients. The average blood pressure of patients is currently greater than or equal to 150. So the null hypothesis in this case says that the mean blood pressure will remain the same even after using the drug, that is greater than or equal to 150. The alternative hypothesis or the research hypothesis says that the mean blood pressure of patients will be less than 150. That means after using the drug it will reduce. To prove his or her research hypothesis, the doctor selects a group of patients and gave them the new medicine for 1 month and then check the results. After collecting the data, the doctor applies the appropriate test to see if he or she can reject this null hypothesis. And in this example, since the alternative hypothesis has a less than sign, so the test will be a one-tailed test or left-tailed test. And this is what is shown over here in this graph as well. So to summarize, the null hypothesis will always compare the two means using either the equal to sign or less than equal to sign or greater than equal to sign. And naturally, the alternative hypothesis will have the opposite signs as shown over here. Moreover, if the alternative hypothesis has a not equal to sign, the researcher will perform a two-tailed test. If the alternative hypothesis has a greater than sign, the researcher will perform a right-tailed test. And finally, for a less than sign, a left-tailed test will be performed. Okay, so far so good. Okay, now we know how to formulate the null and the alternative hypothesis and to gather the data. Let us now see the different categories of tests that you may come across while exploring the domain of hypothesis testing. My dear students, hypothesis tests can be categorized into two main types, parametric and non-parametric, based on the population distribution from which the sample is drawn. If the population is normally distributed, we use some parametric test like z-test or t-test, which we are going to practice in today's session. These non-parametric tests are also known as distribution-free tests, and you can apply them on sample datasets that are drawn from maybe normally distributed as well as from non-normally distributed population data. The tests under these two types are further categorized as one sample test and two sample tests. These one sample test allows us to compare the mean of our sample against our reference mean. These two sample tests allows us to compare the mean of two separate samples, and the samples can be independent or paired. My dear students, today we will use the t-test. You can also use the z-test. Well, this z-test is used to compare means while when the population standard deviation is known and the sample size is greater than 30. And this t-test is used to compare means when the population standard deviation is not known and the sample size is small, like less than 30. My dear students, do a bit of scuba diving at your own time and study this chi-square test and this F test as well. They are used to compare variance. Similarly, do check out for the Mann-Whitney test, also known as the U test, and this Kruskal-Wallis test, also known as the H test. And both of these are used to compare medians of two groups. Okay, anyway, let's keep things simple for the time being. Let's move ahead and talk about some important terminologies related to hypothesis testing. Okay, my dear students, since we are going to practice hypothesis testing using the t-test, which is a parametric test, that is a population from which the samples are drawn is normally distributed. So here is the bell curve of the normal distribution. The mean of this distribution is naturally at the center, and we have already seen that almost 95% of the data resides within two standard deviation, left and right of the mean. Well, with this introduction, let me talk about this alpha as well. This alpha, which is the level of significance. Its value is normally and historically taken as 5%, or maybe some people reduce it to a lower threshold, that is 1%. This alpha is the probability of wrongly rejecting the true null hypothesis, that is the type 1 errors. The other related term with the level of significance is the critical region, which is shown over here in this graph. This critical region is also known as the rejection region. The rejection region is a set of values for the test statistics for which the null hypothesis is rejected. Suppose we have an alpha value of 5% or 0.05. If we are performing a two-tailed test as shown over here in this image, you can split the significance level percentage between both the two tails. So 2.5% or 0.025 over here, and 2.5% or 0.025 over here on the right side. And in case if you are performing a one-tailed test, you don't have to divide the significance level percentage. Rather, you keep that 5% either on the left side or on the right extreme, depending on the whether the alternative hypothesis has a less than sign or greater than sign, respectively. And I think we have discussed this above as well. Now, while performing the test on your collected observations, you compute the you compute the test statistics, which in our case will be the t-score, which can be negative if it falls on this left extreme, or it can be positive if it falls on the right extreme. And finally, you convert this test statistics to its corresponding p-value, that is known as the probability value. Probably this we have seen above as well. And you can compute this p-values using a table, or maybe using some online calculator, and maybe some Python library function. And if the p-value you have calculated falls in this region on the left, or in this region, rejection region on the right, we reject the null hypothesis. And this makes the researcher very happy. And finally, we have different types of errors as well that we can come across while doing the hypothesis testing. And these are due to the bias of the researcher towards either the null hypothesis or the alternative hypothesis. So there are two types of error, type 1 and type 2. This type 1 error means that the researcher has rejected the null hypothesis while it was true. In real life, an example of type 1 error is when a healthy person is incorrectly predicted as sick. On the contrary, this type 2 error is the error that researchers have accepted the null hypothesis while it was false. In real life, an example of type 2 error is when a sick person is incorrectly predicted as not sick or healthy. I hope this makes sense. Let me move ahead and practically do a single sample t-test first. We have already seen this z-score formula, and this is the t-score formula to compute the t-score. Well, my dear friends, this student's single sample t-test idea was given by William Gossett, which he published in his paper under the pseudonym student. That is why this is known as a student's single sample t-test. Well, my dear friends, these z-scores applies to individual values only, and this single sample t-test is its variation that enables us to compare a sample of multiple values to some reference mean. And this is shown in this formula. Note this sample standard error Sx bar in the denominator, which can be computed by dividing the standard deviation with the square root of a number of samples. Let me move on to an example. Okay. Suppose we want to know that a certain species of penguins in Pakistan, their weight is 310 pounds. Let's test this hypothesis using a single sample t-test at significance level of 95%. So let's step by step follow the procedure. First of all, the step 1 is formulate the hypothesis. The null hypothesis is the mean weight is 310 pounds, which is the status quo. The alternative hypothesis is that the mean weight is not equal to 310. It is either less or more. So this is the research hypothesis. First of all, we need to gather the data. Naturally, we cannot check the weight of all the penguins in Pakistan, so we took a random sample of 40 penguins, n is equal to 40, and weigh them. And this is the data that we have got. Then we need to compute the t-score, and we can compute the t-score using this formula which is shown over here. So we are using this formula, calculated the standard error, and this is the t-value, that is minus 3.4186. So this is step 3. We have computed the t-score. The step 4 is we need to compute the p-value corresponding to the t-score. We can use the tables available to us for this. We can use uh, mm, this t-score to p-value calculator that is available online. So the value is minus this. Let me copy this and move on to this link, t-score to p-value calculator. So this is the t-score and the degrees of freedom. We need to provide the degrees of freedom. The sample size is 40, so the degree of freedom naturally will be 39. Since this is a two-tailed test, because we have a not equal to over here in the alternative hypothesis, so I have selected the two-tailed test. And the significance level, let's suppose, is 0.05. Let me calculate. So it is 0.00149. So 0.00149. This is the corresponding p-value. Great. So we are done with step 4. And now we need to move on to step 5, and that is we need to compare this p-value with the alpha, that is a significance level, which is 5%. And since this is a two-tailed test, so we have kept 0.025 over here on the left side and 0.025 on the right side. And since the p-value that we have computed, that is 0.00149, is less than alpha, that is 0.025, so the result is significant and we reject the null hypothesis. And that is we say that the mean weight of penguins in Pakistan is not 310 pounds. I hope this makes sense to you all. So this is how a basic single sample t-test is performed. My dear students, if you are not clear about this, please rewind this part of the video and watch it again, and then move ahead to our students' two independent sample t-test. Okay, so students, two independent sample t-test is used to determine whether or not two population means are equal. This is the formula, and avoiding the mathematical detail of this formula, let us straight away move on to an example for better understanding. So suppose that we want to know whether or not the mean weight of two species of penguins. Let's suppose this time we have decided to compare two species of penguins, Adelie and Gentoo in Pakistan. And let's suppose that we say that the mean weight of Adelie penguins and the Gentoo penguins are equal. And we need to test this hypothesis using the two sample t-test at significance level of 95%. So naturally the null hypothesis is the status quo, that is their mean weights are equal, and the alternative hypothesis that their mean weights are not equal. This is the research hypothesis. Since there are thousands of penguins of these two species in Pakistan, it would be too time consuming and costly to go around and weigh each of the individual penguins of Adelie and Gentoo type. So we take two random samples of 15 penguins from each population and use the mean weight in each sample to determine if the mean weight is equal between the two populations. I hope this concept of two independent samples is making sense to you. In case of single sample, we have a single sample and we compare the mean of that sample with a reference mean. Over here we have two samples and they are independent. So this is the code. Let me run it. So we have one sample of Adelie species and we have the other sample of Gentoo species. The step 2 is we need to compute the t-score using this formula over here above. So let me compute the pooled estimated standard error and the t-value. So this time the t-value is minus 1.25. Let me copy this Open up the calculator, enter the value, and let me check out the degrees of freedom. Number is 40, so we keep it 39. A two-tailed test, let me calculate 0.21847, so 0.21485. Okay. So remember, this difference is because I have kept the degree of freedom wrong. The degree of freedom should be n1 plus n2 minus 2. That means it should be 76. Anyway, so my dear students, we have computed the t value, which is 1 minus 1.25, and since this p value, corresponding p value is 0.214, and this 0.214 is uh, of course not less than this alpha value, so the result is not significant. So we fail to reject the null hypothesis. Therefore, we do not have sufficient evidence to say that the mean weight of the two species of penguin is different. Great. Okay, finally, my dear students, the students paired sample t-test. Uh, we have seen the single sample t-test that enables us to compare the mean of our sample against our reference mean. In the two sample t-test, we have seen the two independent sample t-tests that enable us to compare the mean of two separate or independent samples. Now this is the third category, the paired sample t-test, and this is used in scenarios where we have two vectors and each corresponding element in one vector has a corresponding element in the other vector. And this is also known as dependent t-test and can be computed using this formula. Let's straight away move on to an example. Okay, so this time let us work on a dataset that comes in with the Seaborn library, and the dataset is exercises. Let me load this dataset using the load underscore dataset method of Seaborn. So this is the dataset. I've kept it inside the data frame named df. Just ignore this unnamed column over here. There are 5 columns. ID. This ID column contains the IDs of 30 persons. You can note it moves from 1 to 30. Okay. We have the date column, we have the pulse, we have the time, and we have the kind. Let me check out the unique values under the date column using the unique method. So under the date column, we have two unique values rather, low fat and no fat. I have passed df.dite to this unique method. The output shows that half of the people, 45 of the people, are on low fat diet, whether the other 45 are on a no fat diet. Let me use this unique on the time column as well. Under the time, I have I think 3 different unique values: 1 minute, 15 minute, and 30 minute. So this time is 1 minute, 15 minute, and 30 minute. Let me check out the kind column as well. Under the kind, I have 3 values: rest, running, and walking. 30, 30, 30. So now let me describe this dataset. So this is a dataset or a data frame that actually contains pulse readings after 1 minute, 15 minute, and 30 minutes of resting, running, and walking. Let's check out the pulse rates that were recorded after 1, 15, and 30 minutes of rest, let's suppose. And for that, I have used this df.kind is rest. Let me execute this code. So now we have these 30 values. The pulse rate after resting 1 minute, 15 minute, and 30 minute. Let me just check out the same data after running. Let me execute this code. So these are the observations of the pulse rates after 1 minute, 15 minute and 30 minute of running. Great. And of course we can uh, uh, use a box plot to have a better observation. This gives us some more information. This shows that the pulse rates after 1 minute, 15 minute and 30 minutes of rest. Let me run this graph. And this graph shows us uh, the pulse rate after 1 minute, 15 minute and 30 minutes of running. You can note the difference between the min max and the three quartiles of the two data sets. Okay, so we need to check whether the mean heart rate varies significantly after 1 minute of walking relative to 15 minutes of walking. Let me check this out. Let's check this out. So let me formulate the null hypothesis. So a null hypothesis is that the mean heart rate varies significantly after 1 minute of walking relative to 15 minutes. And naturally, the alternative hypothesis says that it does not change. Step 2 is data gathering. For simplicity, let me consider one of the 6 experimental groups. Let's say this walking and no fat. Let me run it. So this is the data set on which I want to work on. So I have selected these 15 records from the original data frame where the diet is equal to no fat and kind is equal to walking. Note that this first patient having the ID of 16 has a relatively low heart rate at all these 3 points, 1 minute, 15 minute and 30 minute. While this last patient having the ID of 20 has a relatively high heart or pulse rate at all the 3 timestamps 102, 104 and 103. Let's see the distribution of this data using box plot. See the median pulse rate does go up with time as people walk. So it is natural that as people walk, the pulse rate goes up, and it is of course natural. And now the question is this change of pulse rate that we monitored after 1 and 15 minute is statistically meaningful? Okay, so let's check out for 1 minute and filter only those records from the above data frame with timestamps equal to 1 minute. And this is the exact series of pulse that I have got from the above data frame. Great. Now let me convert this to a numpy array. We can easily do that by using the toNumpy function. So this is our numpy array now. The pulse values 1, 2, 3, 4, 5, these 5 pulse values. And similarly we can get another array over here. So this is the data set, my dear students. So we have this data, which is the pulse rate after 1 minute of activity, and this is the pulse rate after 15 minutes of the activity. And let me now draw a scatter plot between these two values, and this is the scatter plot. Great. You can see along the x-axis we have the pulse rate after 1 minute of walking, while along the y-axis we have pulse rate after 15 minutes of walking. And these 1, 2, 3, 4, 5, these 5 dots are the 5 persons. So this dot over here shows that the heart rate of this person after 1 minute of walking was This one, 1 minute of walking was uh, around 91, and after 15 minutes of walking was around 96. Okay, so next is we need to compute the t-score and the p-value. Uh, Let me use the t-test underscore rel method for this purpose. So these are the test statistics that this method has returned. Do go through with the help page of this method. Uh, this is of the stats module of the SciPy library. So this is the p-value. We have got the t-score as well as the p-value in one go, so we don't have to go to the online calculator this time. And let's check out. Let's compare it with the alpha, and and it says that the result is not significant, and the result is not significant because p-value is not less than alpha. Great. My dear students, we have done quickly with the hypothesis testing. I have assumed that you have gone through with these things in your undergrad courses, so I have just done it practically over here because most of the places this hypothesis testing is not done in Python in the undergrad classes. Anyways, we have seen three types of t-test: single sample, independent sample, and paired sample. The last one. Uh, my dear students, in the future, while designing your own machine learning models, you will need these tests. For example, suppose you build a stochastic model in which every time you run that model, you get slightly different results, maybe due to different initial values, different samples, and data points. So you don't always get the same accuracy. And when you compare it with an established benchmark, sometimes your model gives better results and sometimes worse than that particular benchmark. In such a situation, you run your model a number of times, get a sample of your model output accuracies, then use the single sample t-test to compare the sample of accuracies of your model with the accuracy of the established benchmark and get an assessment of the statistical significance. And this is normally what is used in research to prove that whatever your hypothesis it is correct. Okay, so I think that is enough for hypothesis testing. Let us move on to the third and the last section uh, of uh, today's lecture, and that is a journey from variance to covariance to correlation and to regression finally. Okay, so great. My dear students, this section is mainly about regression analysis. Uh, And regression analysis is a statistical method that is used to model the relationship between dependent or a target variable and one or more independent or feature or predictor variables. But before I do a scuba diving in the ocean of regression analysis, let's have a quick recap of certain important concepts that I think we might have covered in our previous session as well. First of all, the variance and standard deviation. My dear students, the square root of variance is standard deviation, which tells us how much a single quantity varies with respect to its mean or how spread out the data is around the center of the distribution. Okay, so this is an example. Please do our mental math to calculate the variance and standard deviation of these three numbers. The NumPy uh, var method and std method, I have used them to calculate these statistics. Let me show you another example. So this is another data set. We are using the mean and STD method of NumPy to compute the mean of the population standard deviation of this data set, which is 5.8 standard deviation. This 5.8 deviation implies that most values are close to the mean. Similarly, if we run this data set, the high standard deviation of 22 implies that the values are more broadly spread out in this case. So this is a standard deviation. Let's talk about covariance as well. My difference variance is a statistical measure for one random variable, while this covariance is used to measure as how the mean values of two random variables move together. Suppose we have two vectors of same length, say x and y, where each element of x is paired with the corresponding element of y. So covariance provides a measure of how related the variables are to each other, and this is the formula for computing the population variance, which can be positive, negative, or zero, indicating that the variables are directly related, indirectly related, or not related with each other. Excuse me. Let me move down to an example. So over here we have some sample weights and some respective sample heights. Let me call the COV method of NumPy, and pass it the two variables to compute the covariance matrix. So this is the covariance matrix. The covariance matrix is also known as the variance covariance matrix, as the diagonal values shows the variance and the covariance as well. One more important point to observe is that the covariance of xy and the covariance of yx is the same. Uh, okay, so this is it. Let me move on to this example of negative covariance. Let me run it. Over here in this covariance matrix, we have this value 6 over here and this value 1.3 over here. The data is of uh, uh, a drug dosage in milliliter and the level of forgetfulness over here. This is the level of forgetfulness, and we have used this to compute the covariance matrix. You can see that in this example we have a negative covariance, while over here we had the positive covariance. And now I think this graph will be clear to you. In case of positive covariance, you will find the scatter plot somewhere like this. The two variables tend to move in the same direction. If one increases, the other also increase. And this is negative covariance. If the one variable increase, the other decrease. And this is the weak covariance. I think we have seen this before as well. So let me move ahead and talk about correlation now. My dear students, the value of covariance range from negative infinity to positive infinity. So it tells us the direction and not the magnitude of relationship. Uh, on the other hand, this correlation or correlation coefficient, this range from -1 to +1. So it tells us the direction as well as the magnitude of relationship between two random variables. Another difference between the two is that covariance is affected by the change in scale, while correlation is not affected by the change in scale. Uh, this correlation coefficient is used to measure the strength of relationship between two quantitative variables. Uh, there are different types, and one is the Pearson correlation coefficient. Like the covariance matrix, we have the correlation matrix. This tells us uh, both the direction as well as the magnitude of the linear relationship between two variables. And this colorful table is an example of a 4 by 4 correlation matrix between four variables: age, height, this cardio fitness level, and hours spent exercising. You can note the positive as well as the negative correlation. Let me quickly move down to an example. Uh, well, this data set shows the daily study hours of the students, and this is the corresponding GPA that the student might have achieved. Let me run the code of this cell and show you how this data is visually plotted using a scatter plot. Along the x-axis we have the study hours, and along the y-axis we have the GPA. And of course, you can note that there is a strong positive relationship between the two variables. Okay, great. You can see the correlation matrix as well over here, and that correlation matrix is showing a value of 0.975. So positive correlation exists. Let's see an example of strong negative correlation as well. This data is of a clinical trial. The drug, this is the drug dosage and this is the forgetfulness level. Let me run the code and show you this. Along the x-axis we have the drug dosage in milliliter, and along the y-axis we have the level of forgetfulness in a patient. Note the negative correlation. As we increase the drug dosage to the patient, the level of forgetfulness reduce. If we give, let's suppose, around 0 ml of drug, the forgetfulness level is around 2.0, and if we give, let's suppose, 6 ml of drug to the patient, the level is around 1.2 or 1.3. I hope this negative correlation is clear to you, and do note the negative correlation coefficient. Great. My dear students, these are the topics that I think I have discussed in the previous session as well, so I have quickly brushed them up. Let me move on to the regression. Let's dig deep in the concept of regression analysis. And before I dive deep, let me give you a brief comparison between the correlation that we have seen above and the regression. Let me straight away move on to an example again. The study and the GPA dataset. Let me execute it and show you a graph. Great. Okay, so the only difference between this graph and the previous one is that I have used the reg plot method, which has plotted a regression line as well. Okay, so we will soon see how we can plot this line using a linear regression model. For the time being, just note that the first difference between correlation and regression is shown over here. Regression can differentiate between dependent and independent variables, while correlation cannot. In machine learning models, the independent variables are also known as the feature variables or predictor variables, and these feature or predictor or independent variables are kept along the horizontal axis, while the dependent variables, this GPA, are kept along the vertical axis. You can note this in this example. And let me reiterate the difference between independent and dependent variables from this example 2 as well. And this is the same example 2 in which we have the drug dosage and the forgetfulness level. Let me execute the code of this cell. Note over here the drug dosage is along the horizontal axis. This is the independent or the feature or the predictor variable, while the forgetfulness level is along the vertical axis, and this is the dependent or the outcome variable. And of course, the forgetfulness depends on the drug dosage. The more drug you give to a patient, the less is the level of forgetfulness. Moreover, this independent variable, this drug dosage, is called predictor or input as well, because you give me the drug dosage and I can tell you the level of forgetfulness from this linear regression line. My dear students, another point to keep in mind is that both these examples, this one and this one as well, uh, are of simple linear regression where we have only one independent variable, which is the study hours in this case and the drug dosage in this case. We can of course have more than one independent or feature or input variables on which this output variable depends. And for that we need to use multiple linear regression models. For example, in this example, this GPA might also depend on the other than study hours, it might also depend on the level of seriousness with which the student has studied, or maybe on the quality of the teaching as well. Okay, my dear students, I think you have a fair idea about the independent and the dependent variables. Let's move on to the second difference between correlation and regression, and that is causality. Regression can measure causality, while correlation cannot do that. Well, this causality is also referred to as cause and effect. It tells us how one variable can impact another variable. In this example 2 over here, you give the drug first and then check the forgetfulness level. So there is a causal relationship from a drug dosage to forgetfulness. And similarly, in this example as well, you study first and then you check for the GPA that you have got. So this is what causality is. That does exist in regression, but it is not there in correlation. Well, the third difference is correlation can measure the strength and direction for linear relationship only, while regression works for both linear as well as non-linear relationships. And maybe in the later part of the machine learning module, we will see the non-linear relationships as well. The fourth difference is regression of xy and regression of yx are completely different, while we have seen that the correlation of xy and correlation of yx are identical. And finally, the graphical representation of correlation is of course a single point, while a linear regression, as shown over here as well as over here, is represented by a straight line. Okay, my dear friends, now $100 question is that how to draw a line that passes through all of these data points. Okay, so fine. This was a quick journey from variance, covariance, correlation, and finally to regression. And this image actually summarizes what we will inshallah cover in our machine learning module of our course. The two main categories of supervised machine learning algorithms are classification algorithms and regression algorithms. Well, these classification algorithms, as the name suggests, are used to classify the data into one of the predetermined categories. For example, filtering emails to spam or ham. The most common algorithms that fall in this classification category are logistic regression, decision trees, random forest, k-nearest neighbor, naive Bayes, and sport vector machines. Well, remember we have used naive Bayes. They are mostly used in text analysis. After the classification, the other main category of supervised machine learning algorithm is regression. The regression algorithms are used to predict continuous values output, like predicting the price of a house, or in the above examples, predicting the forgetfulness level given a specific drug dosage. The commonly used algorithms that fall in this category are simple linear regression, multiple linear regression, and polynomial linear regression. My dear students, we will inshallah cover most of these algorithms with hands-on practice using Python in our machine learning module. However, to give you a flavor of that module, let me just touch upon the most basic and the fundamental model of machine learning, that is a simple linear regression. Okay, so what is linear regression? Let us take the example of study hours and the grade point average. Given these 7 points on a certain Cartesian plane, the question is, how can I fit a line in such a way that the distance between the data points and this regression line is minimum? So the solution lies in the equation of the line, that is y is equal to mx plus b. We all know about this line equation where m is the slope of the line and b is the y-intercept. In this equation, this y represents the dependent variable, that is the GPA, plotted along the vertical axis. This variable x represents the only independent variable, the study hours, plotted along the horizontal axis. If somehow I can find out the slope of the line, that is this m, and the y-intercept, that is this b, then you give me an x and I can compute the value of y. Okay, my dear friends, whenever someone talk about regression, it involves the knowledge of linear algebra and matrices, calculus and derivatives and different error functions. Let me make you understand simple linear regression without the knowledge of these subjects. Okay, first of all, how do we fit a line? My dear friends, let's suppose that these are some of the points. And we have this random line. The question is how I'm going to move this line so that it comes like a best fit as shown in this image. And let's suppose the algorithm is I throw a random line and then start asking the point what do they want, and naturally they want this line to come closer to them. So I pick up a point at random one by one and keep moving this line close to that point until this line is best fitted as per the all of these available points. Okay, so this is how we are going to proceed. Now the question is, how do we move a line close to a point? My dear friends, let's suppose that this is a line and this is a point, and we want to bring this line close to this point. So one option is that we increase the slope. We move this line counterclockwise by keeping this pivot at the same place. We move this up. So we increase the slope. And we know the slope is this vertical distance divided by the horizontal distance. We increase the slope and we get closer to this point. And the other way is we increase this y-intercept. We increase this distance. We increase this distance and we come closer to this point. So these are the two ways to move a line in a Cartesian coordinate. So these two concepts are known as rotation and translation. So the rotation can be in two directions, clockwise and anti-clockwise. If we want to increase the slope, we move in the counterclockwise direction, and if we want to decrease the slope, we move in the clockwise direction, and we keep the pivot at the same place. So this is known as rotation. And the translation, on the other hand, means changing the y-intercept. Suppose this is the y-intercept, we have increased the y-intercept, the line has moved up, and over here we have decreased the y-intercept and the line has moved down. So this is the concept of rotation and translation. And so if we want to move a line, we need these combinations. If we want to move the line upward, we do counterclockwise rotation, increase the slope, or we increase the y-intercept. Similarly, if we want to move the line downward, we do a clockwise rotation, decrease the slope, or we decrease the y-intercept. Okay, so with this background, let me show you this mathematically. My dear friends, let's suppose that this is a line, and this is, suppose the equation of this line, y is equal to 2x plus 3. And this is the point, and we want to bring this line close to this point. So let's suppose that we set a small learning rate, and that is 0.01. And since to bring this line close to this point, we need to increase the slope and we need to increase the y-intercept. So we add 0.01 to the slope as well as to the y-intercept, and this is the new equation that we have got. So this line has moved a little bit up. Remember, in machine learning we have to do something in very, very, very small steps. Let's consider this scenario. Over here, the point is below the line, and of course on the right of the y-axis. This is the equation of the line. So since we want to decrease the slope this time, and we want to decrease the y-intercept as well, so I have subtracted this learning rate from the slope and the y-intercept, and the new equation is something like this. Over here in this example, the point lies of course above the line and on the left of the y-axis. So we need to decrease the slope and increase the y-intercept with this learning rate. And similarly in this scenario, the point is below the line and on the left of the y-axis. So we have to increase the slope and decrease the y-intercept to bring this line close to this point. So these are the four combinations using which we can move the line close to our point. So by keeping this thing in mind, this is the algorithm that we can follow. Note the learning rate is 0.01. We are repeating this step 4 at least, let's suppose 10,000 times. And in each iteration, our algorithm selects a random point, check the location of the point, whether it is above or below the line, and whether it is left or right of the y-axis. And accordingly, we increase and decrease the slope and the y-intercept of the line. And after this step 4 is repeated for 10,000 times, you will get the best fit line. Okay, so let me show you an improved version of this algorithm. So this is the improved version of the above algorithm. Note here we don't have the 4 if-else structures as over here. We don't have those 4 if-else structure in step 4. Irrespective of the location of the point, we simply change the slope and y-intercept using this formula. We multiply the learning rate, that is 0.01, with the vertical distance and the horizontal distance of the point from the line and the y-axis respectively, and add the result to the slope. And similarly for the y-intercept, we add the product of the learning rate and the vertical distance to get the new y-intercept. And due to the positive and the negative distances of these points, the increment and decrement is done automatically. My dear students, I have given sample images and their mathematical formulations. Please spend some time and do the math for clear understanding. And let me show you a piece of code that roughly uses this algorithm to fit a line. So this is X and Y. X contains the study hours and Y contains the GPA, and this is the scatter plot in which we want to fit the line. And over here, let me run the code of this cell as well. And over here, I'm just calculating the new slope and the new y-intercept after executing the above algorithm epochs time, that is 10,000 times. So this code actually computes the slope and the y-intercept of the best fit line by taking certain derivatives. And over here I have just used the plot method to plot 2x values and 2 predicted y values to draw the regression line in the red color. I hope this will make sense to you now. So please go through with this code. It is very well commented. And let me move ahead and tell you another way of fitting the line using the linear least square method. My dear friends, this method or technique works fine if you have only one feature or predictor or independent variable. For multiple features, this will not work. For that, you can use ordinary least square method. And inshallah, we will discuss that in the machine learning module of the course. This is just a bonus part in today's session. So once again, we have this scatter plot. Along the x-axis, we have study hours, and over here, we have the GPA. Well, this is the line equation. Y is equal to C plus mx, where y is the outcome or dependent variable. and that is the GPA, which we want to predict. The two model parameters over here in this case are this C, that is a y-intercept represented by a Greek letter beta 0, and this m over here is the slope of the line. This is normally represented by a Greek letter beta 1 in machine learning language or syntax. So we can write the regression equation like this: y is equal to beta 0 plus beta 1x plus epsilon, where epsilon is the error and we want to keep it minimum. In this scenario, my dear friends, this beta 0 and beta 1 are the two model coefficients, and our main target is to learn the value of these two coefficients. Once we know their values, you give me a value of x, and I will predict it to the corresponding value of y. Great. So let me tell you how we can calculate beta 1. So there is a straightforward formula we can use to estimate beta 1. So over here we have the covariance matrix. At location 0, 1 we have the covariance of xy, and at location this 0, 0 we have the variance of x. So we have just divided it for this formula and we have got the value of beta 1. Great. Now since we have the value of beta 1, we can easily compute the value of beta naught as well by simply readjusting the regression equation a little bit and plugging the values of this beta 1 and the mean of y and the mean of x, and this is what I have done over here in this cell. So this is the value of beta 0. Great. And let me generate the y points and the x points. The y points of the line corresponding to the x points using this, and then I have used this line plot to plot the line. So you see, we have our best fit line. We can now use the model for prediction. Let me predict if our study hour is of 1.5 hours, what will be the GPA, and the GPA over here, it appears that it will be something 1.2 or 1.3. Let's do it over here as well. So for 1.5x, the yi is predicted as beta 0 plus beta 1 into xi. Let me plot it as well for you. So this is it. And of course, the value is 1.33. Great. Well, my dear friends, this is another example for your understanding. The same example that we have seen before as well, that is the drug dosage and level of forgetfulness. Let me run this. This is the scatter graph, and over here I have computed the value of beta 1, and then I have calculated the value of beta 0, and then I have fitted the line. So this is a line fit. Great. And over here I am doing the prediction with the value of 4, what will be the value of level of forgetfulness. So you can do that as well, and I have plotted it for you. Great. Let me show you another example of penguins dataset. So please do go through with this example of penguins as well. This is a good example that I've shown. So after going through with these three examples and the code of these examples, you will have a very crystal clear understanding of what a linear regression is. Remember, my dear students, this was just a bonus part of this session of inferential statistics. I have just covered a single variable along this horizontal axis, the single dependent variable. Inshallah Ta'ala, in our machine learning module, we will do with the multiple features, multiple dependent variables, and we will have fun over there as well. Today was a very long sessions, but I hope it was informative. Great. Okay, my dear friends, that is all for today's session. We will inshallah continue our journey to learn some new topics of this course titled Tools and Techniques for Data Science. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.